Good morning, everybody. My apologies for this. It's 1:20 in the morning here. And yes, I just can't get in to pass the login screen for Meet Cheap. Don't know what's going on, anyway. My first presentation is about GAIA, which is going to revolutionise what we do. Tell me when you're ready to go.
Ready to go, and we're on slide 2.
Slide 2. First thing, they're looking at the current situation. An important number to remember during this presentation is that for main belt asteroids, which is what we mainly look at, 1 milliarc second equates to about 2 kilometres or about a mile on the Earth's surface. So an uncertainty of 1 milliarc second is about, translates to about 1 mile on the Earth's surface. Our current situation with our typical star catalogues is uncertainty in the star position is about 50 milliarc seconds, 50 miles. Typical uncertainty in the asteroid position about 150 milliarc seconds. Put those together, you're sort of well over 100 miles uncertainty in the position of the path. Importantly, for any one event, there's little basis to attribute a path shift that you see in one event to being an error in either the star or the asteroid. There's two sources of errors and there's no way of resolving them. So with our current star catalogues and asteroid ephemerides, we can't improve predictions based on recent observations. Our only way of doing it is doing last-minute astrometry. Next slide. Okay. The situation is going to radically change in a matter of about 6 weeks with the GAIA spacecraft. I'm sure you've all heard about GAIA. That's an image of the technical part of GAIA. The CCD detectors saturate at magnitude 12, but they can measure. They've worked out how to measure down to magnitude 3, and from what I learned in Paris a few months ago, they expect to be able to measure all 243 stars right at magnitude 3 to equivalent accuracy. So we're going to have a really good system coming out of that. Next slide.
You can go right ahead when you say next slide.
Oh, okay. GAIA scanning pattern, it's a rotating thing. The left-hand image is the star distribution in the sky. The right-hand distribution is a 6-month scan. You can see sort of loops within each loop, which is along the equatorial band. That's where it's got the least number of scans. The purple and black are the highest number of scans, which are some loops. GAIA is going to be observing for 5 years, I think it is, 5 or 6 years, to get the full project. Next slide. In this presentation, I'm going to go through some broader issues about GAIA because it's going to revolutionise so much of what we do in astronomy, and I suspect most people don't fully appreciate just what GAIA is going to do. I found it quite an eye-opener. On star positions, it's going to produce microarc positions. It's actually about 10 microarc second positions, proper motions and parallaxes down to magnitude 20. That's about 1 billion stars, give or take. Radial velocities and spectral types down to magnitude 16. It's got that's 150 million stars. GAIA actually has a spectroscope on it, which is looking at all the stars sufficiently bright. It's only looking at a small part of the spectrum, but it's sufficient to do radial velocities and spectral typing. Element abundances for stars brighter than magnitude 11. Positions and orbits of asteroids and TNOs to somewhere around about magnitude 20. And this is at the micro arc second precision. Next slide. This is a plot which shows the estimated or the intended accuracy against magnitude in the final catalogue. The bottom line, the brownish line, is proper motions. You can see at magnitude 15, it's about 13 micro arc seconds per year. Position is the blue line, which is in the middle at magnitude 15. Position around about 20 micro arc seconds. And parallax 25 micro arc seconds. At 20 micro arc seconds is 0.02 of a milliarc second. So think of that as 0.02 of a mile, a 50th of a mile, which if I remember rightly is 30 yards. That's the type of precision they're expecting to come out of GAIA. And on the star side of it, if you could predict the position of the asteroid accurately, the uncertainty of the star position is going to give you an uncertainty on the Earth of about 30 yards. Totally different game that we're in this environment for observing these occultations. Fundamentally different. Yeah, looking at some other aspects with GAIA, which I think it's worthwhile to go through these things, just to have a general appreciation of what GAIA is going to do to astronomy as we know it. GAIA impact on variable stars. Now, the bottom line here in red, the current AVSO index catalogue, and that's lists all the variables, has 342,000 entries. Large number. GAIA is going to do multi-epoch photometry for everything brighter than magnitude 20. Will detect variability on timescales between seconds and about 5 years. They estimate detecting about 18 million stars, variables, including 5 million Cepheids, 3 million eclipsing binaries, with precise physical and orbital parameters for about 10,000, 300,000 rotation induced, 250,000 mirrors, 100 to 200,000 delta scuti, 70,000 RA there, 20,000 supernova. The current AVSO index catalogue has hardly scratched the surface of what they expect to come. GAIA impact on double stars. Down the bottom there, Washington double star catalogue, 135,000 pairs. The USNO interferometric catalogue, 83,000 pairs. They estimated that GAIA will have 700,000 radial velocity orbits, 800,000 radial velocity plus astrometry orbits, 2 million astrometric orbits, 4 million non-linear proper motion systems, and 40 million resolved binaries. And it's going to resolve all binaries with separations greater than 20 milliarc seconds with a moderate magnitude difference. Huge change there. So it's important we get a handle on how GAIA is going to affect what we do over the next few years. So next slide. The GAIA data release. The first data release is going to be on 14th September. That's a definite date. That data release is a limited data release, and there's two components, and it's important to understand the difference between the two. The first component, which is going to have something of the order of about 1 billion stars, is the positions and G magnitudes for all stars with acceptable formal standard errors on positions. So that's all stars down to magnitude 20, positions and magnitudes, but no proper motions and no parallaxes, which is an issue. The second, and I believe it's going to be a standalone catalogue, is they worked out how they could combine the data from GAIA with the data from Hipparchus and the Tycho 2 component of Hipparchus to do a solution for the whole astrometric solution for the stars which are observed in both. So be able to, for the stars which are in Tycho 2 and Hipparchus, they'll be able to issue what they call a 5-parameter solution, that is positions, parallaxes and proper motions. And it's going to be called the Tycho GAIA solution. And that goes down to about magnitude 11.5. Second release, August, September next year, is a 5-parameter solution that's positions, parallaxes for single stars. Integrated blue and red photometer magnitudes, so you have proper magnitudes for the stars, and radial velocities for stars which have got constant radial velocity. Next slide. Third release, your summer of 2018. That will increase the data resolution to orbital solutions with system radial velocities for binaries for periods between 2 months and 3/4 of the observing time. Object classifications and astrophysical parameters together with spectra, and mean radial velocities be released for those stars not showing variability. Fourth release in 2019, you'll get variables, and importantly for our interest is solar system results will be released with preliminary orbital solutions and individual epoch observations. On that, but you can assume that all currently numbered asteroids and a fistful of the unnumbered asteroids will be fully determined out of GAIA. Because it does all the asteroids down at about magnitude 20. And non-single star catalogues will be released. Next slide. So from 2019, it seems the final data release will be 2022, which has got the full solutions for everything, including an exoplanet list apparently. So that's what we can expect to come out of GAIA. I don't know how much of that is news to you guys, but I found when I started reading up on it, there were things there which I had not appreciated. So what's all this mean to us? So next slide, issues. With the first data release, we will have proper motions and parallaxes for stars bright and about a magnitude 11.5 in the Tycho GAIA catalogue. So long as they're not part of binary systems or variables, and if the stars in a double star system have its own problems with that anyway, we will have proper motions and parallaxes for the stars we most commonly currently observe. For fainter stars, we have positions but no proper motions or parallaxes. Although for most of those faint stars, parallax is too small for us to worry about. And there'll be no entries for stars that show evidence of a companion. Next slide. Now for stars in the Tycho GAIA solution, there's a bit of a table here which gives you an indication of the number of stars involved, the astrometric accuracy of position in microarc seconds, parallax, which we're not too worried about, and proper motion. And proper motion is probably the one area which we have the greater concern about. But The Tycho GAIA solution we only need to use for the first 12 months, which would be about 2 years from the GAIA epoch. If you work through the numbers in this, for events which occur within 2 years of the GAIA epoch, which is about the beginning of last year, the positional uncertainty at magnitude 6, about 0.5 milliarc seconds, Mag 9, 1.1, Mag 12, 3.5 milliarc seconds. And remember, for a main belt asteroid, 1 milliarc second corresponds to 2 kilometres path movement. So with the Tycho GAIA solution, the star position becomes effectively an absolute known. You know exactly where the star is in the scheme of things. It's all about the asteroid. But what about all the other stars? With GAIA 1, we will have positions but no proper motions for stars down to magnitude 20. What we've worked out we can do is we can derive proper motions using the imaging epoch positions from UCAC4 and possibly PPMXL. The typical uncertainties in UCAC4 at around about 2000 is 20 milliarc seconds at magnitude 12 and 50 milliarc seconds at magnitude 15. Given the 15-year interval between UCAC and GAIA, this reduces to a proper motion uncertainty of about 1.3 milliarc seconds at magnitude 12 to 3 milliarc seconds per year at magnitude 15. Remember, 3 milliarc seconds is 6 kilometres, 3 miles, 4 miles. Again, if we add in the UCAC4 derived proper motions, we know exactly where the star will be. So, in a practical sense, with GAIA, if we do a bit of work with UCAC4, we will know exactly where the star is without having to wait for GAIA 2. Next slide. This is star uncertainties in long term. This is just a plot out of their documentation. You can see that the brown line is magnitude 16, 2090, and I'm not sure how many of us will be alive then. I don't expect to be. But the uncertainty is only a kilometre or 2 kilometres, whatever. Next slide.
Tap that screen once and then tap the laptop.
So, a bit of a the summary for stars, the situation with stars, GAIA 1 will provide star positions within uncertainties within 2 years of GAIA epoch. Well, you can read the figures there. They're triflingly small to what we have at the moment. The star is brighter than 13. Uncertainty in path location due to the star uncertainty will be less than 10 kilometres. Magnitude 9 will be a mere 2 kilometres. Importantly, for the fainter stars, I've built into Occult now a routine to derive proper motions for GAIA 1 release using UCAC4. Visia has a system called TapVisia, and I've been working with them and developed some routines there where I intend downloading the GAIA catalogue down to magnitude 14 and derive proper motions from UCAC4 and create our own special catalogue with GAIA 1 UCAC4 derived proper motions. And the file size will work out as about 1 gigabyte. Whereas the Tycho GAIA solution, that'll be about 140 megabytes. GAIA 2 will have proper motions and will consider reduced uncertainties. So GAIA, as of September, is going to fix up our problems with stars. So let's go to the next slide, which is asteroids. Because asteroids is where our biggest uncertainty is going to be. The asteroid orbits will not be available until the fourth release in 2019. Although from the meeting I went to in Paris in April, that we might be able to get stuff before then, don't know. Past occultations provide accurate offsets from stars. The numbers are less than 10 milliarc seconds. Well, you can read those numbers there. If we have proper motions available for the stars, we can derive Gaia-based positions of the asteroids for those past occultation events. And that means that if there are enough observations of an asteroid, we could update the orbit from our past asteroidal occultation observations. This will presumably be a task for Steve. Looking forward to it, Steve?
Yeah. Yeah, totally.
Now, situation for asteroids, and for the last part of this discussion, I'm excluding TNOs because there's, they're that much further away, a separate set of issues. Data release 1, no Gaia proper motions. Old positions are limited by the accuracy of old catalogues, but observations made in the last few years were less affected by proper motion issues. Therefore, there's an opportunity to improve current predictions made by using astrometry from asteroidals made in the last 1 to 3 years. Next slide. Data release 2 will have Gaia proper motions. That means that the old positions will be limited only by the accuracy of the astrometry derived, relative astrometry derived from an occultation. We can use our backfile of astrometry from occultations to improve the orbits, and that goes back to the late 60s. But the full improvement for the asteroids will not occur until data release 4 in 2019. So we do have a period of time where we still have some uncertainties. How do we handle that? Next slide. The immediate situation for asteroids. The main belt asteroids, positional observed minus computed, generally change slowly over a period of months. You're in the same part of the orbit. Generally speaking, there's not large changes, and the asteroids we're dealing with, the orbits are fairly well defined anyway. That means an observed offset from a recent occultation will provide a reliable indicator of the offset for the next occultation. That's something we've never been able to do in the past. That means that observations from several previous events will provide a trend that we can extrapolate. Next slide. The implication of that is we need to encourage observations of as many events as possible, even if the probability of an occultation is small, to establish the recent offsets of asteroid ephemerides. For stars by the magnitude 12, we should be able to have a combined uncertainty of star and asteroid less than 10 milliarc seconds, which is less than 20 kilometres, 10 miles. Next slide. Then there's the USNO Flagstaff Astrometric Scanning Telescope, completely automated 20 centimetre. Steve Preston could probably talk about that at some stage, but they may be in a position to provide astrometry of selected asteroids using the GAIA reference frame. And that has the potential to provide the most reliable source of positions for asteroids. But I suspect there's going to be a range of issues with getting appropriate levels of cooperation for a range of asteroids. That require some management to get what we need out of that. Long-term situation for asteroids. So looking 2019, past predictions to be accurate to about 1 kilometre. It's sort of unbelievable, isn't it? We'll be able to plan an event with certainty, apart from the weather. The focus will move from observing anything that happens nearby to efforts to studying particular asteroids. Our focus is going to change inevitably. And throw into that, we will need to develop a capability to incorporate shape model predictions to predict path edge locations. And maybe we'll do grazing occultation profiles for asteroids. An interesting thought. Next slide, getting towards the end of this. Other issues for asteroids. We will need to start identifying asteroids that we should focus our attention on. Issues which come to my mind, and it's open for discussion, is things like minor asteroids, asteroids with shape models, asteroids having some other characteristic of importance, e.g. members of certain class of asteroids, whether that be composition, orbit type, or some other thing. Next slide. Again, at the moment, we just tend to go out and observe anything that's around because they're not so common and the uncertainty of it. We need to start thinking about the frequency of events involving a selected asteroid. For example, do we focus on asteroids when they move through star-rich regions of the sky, such that we get numerous events over a few months at different rotational orientations, which we can then match to shape models? It's going to affect our planning for these events in terms of being selective. Next slide, summary. GAIA 1 will largely eliminate star positions as a cause of uncertainty. The asteroid will be the largest source of uncertainty until GAIA 4, but we could get path locations to better than 20K. And we need to develop a strategy for selecting events we want to focus on. Now, a final bit which I haven't got on the slides here. Last week in Europe, they successfully recorded an occultation of a star by Pluto. I think they must be about between 5 and 10 sites recorded it. A lot were clouded out. That event had a special significance. They actually managed to extract a pre-release GAIA position for the star, the one and only pre-release star position, and we derived a proper motion using UCAC4, and the relative position of Pluto and the star was accurate to about 10 milliarc seconds. And the final slide is, it's all over. Happy to take questions.
Yeah, go ahead.
Good day, Dave. This is Bill Hanna. I was wondering, do the GAIA people expect to find the so-called Planet 9 should it actually exist?
they expect to find new asteroids. I think if it's brighter than about magnitude 20.3, it'll be recorded. But the planet 9 or 10 or whatever number you want to give it, in the last I saw they're talking about being a huge distance out, so.
Oh. Joan? Dave?
Okay, yeah, I just have two remarks. Let's see. Of course, the important thing is that we're going to have a lot more occultations to observe, and I think we need to make more of an outreach to the astronomical community to try to get them excited about this, to make the investment in the somewhat arcane equipment that we use that most astronomers don't have, to encourage them to make these observations, because now the discouraging thing is you try a bunch of events from your observatory, and something of the order of you're only successful maybe a third of the time, and the other times you have no occultation because the prediction's too uncertain. But we'll be able to tell which events you'll really have at your observatory, and if you have a mobile capability, you'll have a lot more opportunities to use your mobile equipment. And one of the things I advocate people to do is to set up a remote station at their home observatory and then go mobile with their telescope. Then they don't have to put any equipment in danger. And that way you can get two cords instead of just one, and that's hugely important, as Brad pointed out in his presentation. Oh, sure. That's another topic. I agree. And then we're working on that. Yeah. Of course, yeah. So, but you're going to have more bright events and different things, and so, Joan?
However, I'd like to point out, since we will be able to provide very good predictions, we will reduce the number of people who give up, because after 3 times seeing nothing, they're just tired of this. It's disappointing. You get more people who, even if you only have one station, if you have 4 people who each have one station, and you can predict the location to 20 kilometers, 10 miles, there's 4 more observations. And I think that's going to be where we really see the real growth.
Yeah, when we meet with people at NEAF, and also when I do my talks at various astronomy clubs, I run into large numbers of people who used to work with David 20 years ago, but I gave up because I had 7 misses in a row. It would be really nice if we have a brochure we can start handing out at like the AL meeting and future NEAFs and all, that says how GAIA is going to help us and why you might want to get back into this again.
Yeah, right. And the
Can I also add to this? Can I also add to this that at the moment we don't generally predict anything less than about 20 or 30 kilometres diameter. With the type of accuracy we're going to have, it'll be sensible for us to generate predictions of the brighter stars certainly down to 10 kilometre asteroids and maybe 5 kilometres or smaller, which means the number of events are going to go up hugely.
Including 4 stations or 3 stations that we set up with Mighty Minis, but none of us got a hit because the prediction uncertainty. But we'll be able to do things like that then. But anyway, the other thing I had, you talked about improving the predictions for the asteroids. I mean, that's going to be the big problem until 2019. And you talked about FAST. Observations for doing that, and the other thing is, of course, using other occultations, especially past occultations, and to predict offsets and then predict trends. And of course, if you can get Supposedly if you've got 3 really accurate observations from past occultations, then you could even predict the orbit. You don't need just offsets. But to really do it, you want 5, 6 accurate points at least, so you can do a little bit of statistics. But the
So I think you feed the data into Steve, you put through his orbit solving software and solve the whole problem.
Yes, yes, and then the but the thing is, the fast observations they're made just with a 20 centimeter telescope, and they're kind of limited in their accuracy. The reason that's effective is because they make so many observations. But the thing is, with the more accurate star net now that we'll have, then it'll be more effective to make observations with the larger telescopes, with the 61-inch astrometric telescope at Flagstaff especially, but with other telescopes like the ones in Brazil and even the 24 or the one at Table Mountain. And so their astrometry will become important, and we can use those as points to augment the dearth of past occultation observations to get really accurate orbit updates before 2019.